Uh, Hello, everyone. Um, my name is Dohoon Kim. I'm from PSC. Today, I'm going to talk about formal verification framework for circuit constraints using Horror logic. So let's start. So today, my talk is about first is state of formal verification of ZK circuit programming, and second, existing approaches and frameworks for formal verification. And third, I'm going to propose new formal verification framework grounded by Horror logic. So this work is joint work with PLRG Lab in KAIST. And the idea was inspired by the talk with Kang-Wook Lee at PLRG and also my colleague Suwon from PSC team. Yeah. So let's start. So in advance, let me just briefly talk about what is arithmetic circuit. So in order to generate ZK proof, we need arithmetic circuit that encodes constraints. So these constraints are usually represented as polynomial equations over a finite field. And developers usually write their constraints in domain-specific language. And the DSL compiler often builds arithmetic circuits based on the constraints. So there are lots of DSLs for now. For example, like Circom, Cairo, NOR, and all other things. And there is a security issue. So there's a security issue in the circuit when the constraints are incorrect. So this kind of security holes in constraints can let malicious prover generate the valid proof. So this security of zero-knowledge circuits is very critical matter. So these are well-known famous security issues in the zero-knowledge circuits. So there are lots of security issues for now. So we can ask a question, what is secure circuit and how can we prevent these kinds of security bugs? So let me start with defining what is the secure circuit. So first, the secure circuit, in the secure circuit, constraints should be uniquely satisfiable. So this uniquely satisfiable means that given the constraints and the given public inputs, there should be a unique witness to satisfy these polynomial constraints. So if constraints are not uniquely satisfiable, malicious prover can generate valid proof without knowing the valid witnesses. So these kinds of unique satisfiability problem usually can be handled by algebraic methods and formal verification methods. And second, circuit constraints should align with the specification of the developers. So circuit constraints should enforce the desired properties, the intended specification properties of the developers. And if constraints cannot enforce this specification, there might be a misinterpretation of the circuit and also the misuse of the circuit. So these kinds of specification problem can be handled by formal verification methods. So this is the picture for what is depicting what is the secure circuit. The constraint should be uniquely satisfiable, and it should express the desired specification property correctly. So let me first go through the approaches on the satisfiability problem. So most naive way to approach this kind of problem is to directly solve the system of polynomial equations to decide the satisfiability. So these kinds of problems are usually start by computing the Grabner basis of the polynomial ideal generated by the polynomial constraints. So I'm not gonna talk deeply about what is Grabner basis and what is polynomial ideal, but just think that polynomial ideal is just an algebraic structure, and the Grabner basis is just a generating set of this ideal that has very unique, that has very special property. So if we are given Grabner basis, one can apply various algebraic methods to solve the system. So in this paper, like on the satisfiability of polynomial equations over large prime fields, the authors explore various algebraic techniques to solve the polynomial systems using Grabner basis. So the most notable approach was that they apply primary decomposition method by using Grabner basis. So this primary decomposition method is also based on very, very math-heavy things, but it is just decomposing the problem into the smaller subproblems using the Grabner basis, and then solve each subproblems. So this looks really fancy, but it has a quite poor performance and scalability issue because when computing the Grabner basis of the polynomial constraints, we usually consider this kind of field polynomials. So I'm going to talk about what this field polynomials is in the later slide. And this is another approach. So second one is, it is based on the combination of SMT decision procedure and the algebraic methods. And they use like conflict-driven class learning like decision procedure in this paper. So they also used Grabner basis, but this also has the poor performance and scalability when computing Grabner basis because of the field polynomials. And the third one, so this also combines the SMT decision procedure with algebraic methods, but they have a kind of performance breakthrough compared to the prior approaches. So the difference between the prior approaches was that in prior approaches, in order to ensure the completeness of the Grabner-based testing, they usually take into account into the field polynomials into the Grabner basis computation. But in this paper, they removed field polynomials in Grabner basis computation and defer the completeness of the test when finding zeros of the polynomial systems. So they were quite more faster than the prior approaches, but still, finding zeros of polynomial system was quite very, very computationally heavy things. So until now, we have seen the approaches on satisfiability problem, and now let's see the approaches on the specification problem. So in this paper, certifying zero knowledge circuits with refinement types, they introduces a new DSL called CODA for formal specification and verification through proof assistant like Coke. So they were very powerful because that kind of proof assistant can verify every desired property of the program that developer wants, but it is very hard for developers who are not familiar with this kinds of proof assistant programming. So this diagram is the overall formal verification approaches. So the x-axis is for the usability of the research, usability and the performance. And this vertical line indicates the capacity. It means that what problem they are trying to solve. So in satisfiability problem, there are several approaches now, but in the specification problem, we have only, for now, as far as I know, there's only CODA DSL that tries to solve this problem. And this CODA DSL is quite not very easy to use for the developers who are not familiar with this kind of proof assistant. So I thought that there are some kinds of gray zone here that is trying to solve specification problem and very usable for common developers. And also there's another hidden metric of these approaches. So these approaches usually focus on the security guarantee after the construction of the circuits. So these approaches are usually applied for already constructed circuits. But this CODA DSL, they try to guarantee the security by construction because they are providing a DSL to program the secure circuit. So I wrote the wish list of this gray zone. So what do we want? So we want more easier to use tooling, and also it should provide formal specification and verification framework, and it also should provide guarantee by construction. So inspired this, my hopes on this new research, I tried to propose new framework based on this world logic. So as we saw, we require better tool for formal specification and verification of the circuit program. And we also require easier automatic and systematic formal verification method to solve these kinds of specification problem. And the Hoare logic system, I will explain what is Hoare logic system in a later slide, but this system serves as a fundamental framework for verifying the correctness of general computer programs. And this is generally based on the first order logic in computer science. So, okay, let me briefly explain what is Hoare logic. So Hoare logic is essentially based on this Hoare triple. So this Hoare triple consists of precondition, program, and postcondition. And this precondition and postcondition, they are just logical predicates. So they are logical predicates in the first order logic statement. And what they state is that before program execution, the predicate P is true. And what this postcondition Q states is that after program execution, predicate Q is true. And these collectively says what is that if program starts with P, predicate P true, and the program executes and terminates, then predicate Q becomes true. So this is the very simple example of this kind, describing this Hoare triple. So before the program, if the variable x is bigger than 0, and in the program, we simply add 1 to the variable x, then after the program, the post conditions might says that variable x should be bigger than 1. So this part, if program starts with predicate P true, and program terminates, then predicate Q becomes true, is usually the specification of the program. And okay, we saw the Hoare triple till now. And the Hoare logic is, they are just a logical system, and they are composed of axioms and these kinds of inference rules. So you can see that in axioms and inference rules, all the basic elements are the Hoare triple that I described in the prior slide. And the Hoare logic system decides whether program satisfies the desired post condition from the precondition and the program with these kinds of axioms and inference rules. So there is already a programming language framework based on this Hoare logic. So it is called Zafny. This is just a programming language framework for writing verified program, and it is also grounded by the Hoare logic. So if developer writes the program in Zafny, automatic verifier tracks the correctness of the program based on the Hoare logic and with collaboration with the SMT solver. And since Hoare logic is, as I said, generally it is based on the first order logic, the developers can write their own assertions or invariants, like kind of loop invariants and lemmas to assist this Hoare logic system. So my question was, can we adapt this kind of Hoare logic to write verified circuit? So we can imagine like Zafny like circuit programming DSL. So like we can augment the existing DSLs like Circom with automatic verifier that is also grounded by Hoare logic like Zafny. But the difference with Zafny is that Zafny is for verifying the general computer program, but we are focusing on verifying the correctness of polynomial constraints inside the program for our desired specification. So like irrelevant part with the constraint generation, like irrelevant part like witness generation parts can be just ignored when in the verification procedure. And also, as in like Zafny, developers can assist Hoare logic with their own assertions, loop invariants, and lemmas too. So let's see one example. So this is the circum num2 bits template. So this template inputs the parameter n, and it has input signal in and the output signal out. So out is an array. And this num2 bits template is just converting this input in into their bit representation and contain them to this array out. So, and this num2 bits template is useful when we want to constrain that a certain input should be smaller than 2 to the power of n. But have you ever thought that this template is really constraining this post condition correctly? Like we always believe that, but we want to write the verified program for this desired post condition. So let's reframe this circum template into the Hoare logic framework. So we have a precondition that n is less than equal to 254. That is based on like some other facts, but and this template become a program. So, and the post condition becomes that the input should be smaller than 2 to the power of n. And it can say that if p becomes true, if p is true, and after c executes, then q becomes true. So actually, this num2 bits template is not itself executed program, but just let's imagine that this is a program for, program. So now we can augment this circum template like this. So it is Daphne style programming syntax, but so we can write our precondition with requires, and we can write post condition with ensures clause. And in order to constrain that this input should be smaller than 2 to the power of n, we can use these kinds of loop invariants. So let's see more closely that, so this part, the loop is the most important part. And inside the loop, we can just ignore that witness generation parts. And we have one constraint that ith element of out array should be equal to 0 or 1. And based on that, we update the variable lc1 and variable e2. And the developers can write in the loop invariant that variable e2 should be always equal to the 2 to the power of I, and variable lc1 should be less than 2 to the power of I, and I is always less than equal to bits. Then, at the end of this loop, we can say that this lc1 is less than 2 to the power of bits based on this loop invariance. And after the loop ends, there is a constraint that lc1 should be equal to in. And now we can say that this in is smaller than 2 to the power of bits. So this kind of inference rules are very crucial in Hoare logic. So yeah, in this style, like developers can assist Hoare logic system with their own loop invariants in this fashion. So in order to achieve this, we propose new extended Hoare logic system. So now we can think about this new extended Hoare triple like this. So we still have precondition, postcondition, and instead of just general program, now we have a constraints. And now the precondition and postcondition, they are the polynomial constraints augmented with first order logic. And what they state is before program execution, this P is satisfied. And after the correct program execution, this Q should be satisfied. And collectively, they say that if constraints P is satisfied and program terminates, it means that C is now satisfied, then it should induce that Q is true. So in extended horror logic also, we ignore, as we saw, we can ignore the witness generation part of circuit inside the verification procedure. And also, we should cover polynomial constraints. And polynomial constraints is not natural inside the general program. So it is not basically supported by the original horror logic. So we should extend the horror logic rules in order to handle these kinds of polynomial constraints like this one. Yeah. So still, we have only one extended rules, but maybe we can have more and more rules after the research proceeds. So this is the recap. Now we have a precondition and circuit constraints. And the first question was, is precondition and circuit constraints can be uniquely satisfiable? And the second question is that, is precondition and circuit constraints can induce our desired postcondition? So it is our specification problem. And as we saw, this unique satisfiability problem can be handled with Grabner basis or like elimination theory, like various algebraic methods. And these kinds of specification problem now can be handled with this kind of extended horror logic or new Coda DSL from the previous slide. And key takeaways is that now we can classify the circuit verification problem into two problems. So one is unique satisfiability problem, and the second one is the specification problem. And we can adapt horror logic to solve these kinds of specification problem. And extension, so we extended the horror logic to embrace these kinds of polynomial constraints. And we also proposed like new systematic and automatic verification framework for circuit programming based on the horror logic. Okay, so this is end of line talk. Thank you.
And now we have like 3 minutes Q&A time. Does anybody have any question?
Do you have a repo of examples for Zafny code with constraints?
So this is in very early stage and still in POC, so I haven't open sourced it yet, but I will soon open source this repo too, yeah.
Thank you.
Thank you.
Does anybody have more question? Okay, thank you.
Thank you.